Hey everyone, welcome back. And in this video, we are going to be looking at a few momentum examples together. So in the previous video, we went through the definition of momentum and kind of the motivation for why we're studying it. And so today I hope to show you a couple examples where this equation of momentum can apply itself, and we can see that it can be pretty useful. Okay, so in our last example, we had a rifle firing a gun, or a rifle firing a gun, no, a rifle firing a bullet, and we said that momentum is conserved. There is this explosion that happens inside the chamber when we pull the trigger, and the gun recoils with a certain velocity, and the bullet fires with a certain velocity. And we were able to actually find the recoil velocity of the rifle by measuring the speed of the bullet, knowing the two masses. So pretty interesting example. Now we're going to continue this example in a somewhat logical fashion. Normally, we're trying to fire into a target. So let's say we have this block of wood, or that we're firing at, and we want to see how fast um, this block and bullet are going to move. This could be done in terms of like a ballistics testing. This is if you're looking into forensics, this is similar to what they'll do when they'll fire the gun into a block, and they'll be able to see different things that come up from that. So the bullet, whose mass is 50 grams, as we discussed before, fired with a speed of 1100 meters per second. So it's leaving the chamber here with a speed of 1100 meters per second, and it's in the x-hat direction. Now, we don't actually need to worry about the gun anymore at this point, because our system now, when we look at the collision between the bullet and the block over here, only relies on the bullet and the block. So if we were to redefine our system now, we would say that our system is the bullet and the block. And this is important. So this means that the mass of the gun no longer matters for us. And the fact that everything was initially at rest, we don't actually care about that. All we care about is the fact that the bullet's traveling at 1100 meters per second, collides with this block, and we want to figure out how fast, what's the V final of this collided system here. And so again, momentum can be conserved in this idea. So our initial and final momentum of the system, our initial momentum is going to be just in terms of, I'm going to do these in slightly reverse order because I think it's easier to understand them that way. The initial momentum of the system is our combined initial momentums. We have our initial momentum of our bullet and our initial momentum of our block. And momentum is mass times velocity, as we talked about in the last video. And in general, mass times velocity is a vector. So our initial momentum for our bullet is our mass of our bullet, which we had was 50 grams, and we found actually the momentum of the bullet in the last problem is 55 kilograms meters per second. So we've already done that calculation, so let's go ahead and just reuse that number. So our initial momentum is 55 for our bullet, and our block is, it's at rest. We haven't hit it with anything, so it's just resting on the table, so it doesn't have any momentum initially. And so this means that our initial momentum is just this 55. All right. Now, yes, the gun is recoiling, and the gun would have a momentum of negative 55. But because we're not including the gun in our system, it doesn't go into the calculation. Right? And so it's a little bit different than the last problem in terms of that. So that's it. The initial momentum of the system being the block and the bullet itself, is going to be 55 kilograms meters per second. If we included the gun, the rifle, in this system, then our momentum would be 0, because the momentum from the bullet and the momentum of the gun would cancel each other out. All right, but since our system is the bullet and the block, we do have a positive momentum. And then, so what's our final momentum of the system? Well, our final momentum of the system has to equal our initial momentum of the system. This is a conservation of momentum thing. And this conservation of momentum is always true if we don't have any other external forces acting on the system. So this is actually pretty important in this problem. Something that it doesn't say in this is whether or not there's friction, but we're not really concerned about what happens after the collision. What we want to know is that these collide and how fast are they moving. Yeah, there might be friction that will slow this thing down, but we want to know what is the speed immediately after the collision. So it doesn't actually matter if there's friction here or not. But generally speaking, momentum is conserved as long as there's no external forces acting on our system. So there's not a third object coming into the system that's interacting with it or taking some of the momentum away. And so we can say P final equals P initial, and so our P final is also going to be 55. All right. Well, now let's go back to part A. And part A said, if the bullet embeds itself within the wooden block, how fast will they move off together after the collision? So we know our final momentum already is 55. And our final momentum is going to be made up of the momentum of the bullet and the block moving together. Now, they're not, once the bullet embeds itself in the block, we can treat it as one object with one mass. We have a little m and we have a big M. Oh, yeah, sorry. When I was talking about this earlier, yes, the gun is 6 kilograms. The large wooden block also happens to be 6 kilograms as well. So this mass here is actually important. So I misspoke earlier, but that's fine. So the mass of the gun, yeah, that doesn't matter anymore. But the mass of the block does matter. So P final is 55. And I'm gonna keep the units in here just so we can see what happens with them. And the bullet and the block together, this is mass times velocity. Well, what's my mass? My mass is the mass of the bullet plus the mass of the block, 6. So 0.05 plus 6 times our final velocity. All right, and so I basically take 55, divide it by 6.05, and these units are kilograms. So we're again going to see that when we divide, the kilograms are going to cancel the kilograms here, and we're going to be left with a velocity in meters per second. So the units do work out nicely. And then this one will give us a velocity final of 9.09 meters per second. So pretty similar to our recoil velocity in the last problem, which was 9.1. It's a little bit less. And the reason it's a little bit less is because we have a slightly bigger mass moving. The momentum in the first problem that we did was carrying the gun backwards, but there was no bullet inside of the gun anymore. So it has slightly lighter mass. I mean, the difference in this is not very much. 0.07, we're looking at 0.08. So pretty small percentage of the entire velocity. But yeah. So this is how you would do any type of collision problem. And anytime any two objects are colliding with one another and momentum is conserved, you can do this type of thing where we just combine the masses together just like this. And that's the trick to solving these problems. All right, and let's look at another example here. I've got a few more today that we're gonna go through, so we'll see a bunch of different examples. Here we have a railroad car with a mass of big M, and that'll tell us what it is, traveling at a speed of v, strikes an identical railroad car that is at rest. Cars lock together as a result of the collision. What is their speed after the collision? We're going to have a similar idea here where we have one railroad card, another railroad card. There's a collision between them, and they stick together and they move at one speed. All right, and so let's just draw a little picture here. We got our car number 1, which has a mass, and it's traveling this way with a speed of v. And we have another car here, which has a velocity of 0 and a mass m. And then after the collision happens, they connect, as railroad cars do, and they're moving with some final velocity. Initial. And we're going to be able to figure out what the speed is of v final relative to v initial. So they don't actually tell us what this speed is. So we're going to leave everything in terms of variables, but v initial is going to be this variable, which we're going to denote as v, and v final we're going to try to solve in terms of v. All right. So even if you don't have numbers, it's fine. We can just keep everything in variables. You don't have to be scared of them. It's solving it out is quite the same. All right, so what's the idea here? Well, again, let's start with our conservation of momentum equation. Our initial and our final momentums are going to be equal. Well, this is my initial picture right here. This is my final picture right here. Initially, I have car 1 that has momentum, right? So my system is going to contain both these cars. And in here I have the same system, right? But I can look at these in two different pieces here. This is one piece, and this is the other piece. This has a momentum of 0, it's not moving, and this has a momentum of big M times V. So my initial momentum, I'm just looking at this guy right here, it's going to be my first car times its velocity plus my second car times its velocity, which happens to be 0. And so this term we don't need to include. And I'm just going to work down on the left-hand side of my equation. So this will be m times v. Now, what is this equal to? Well, it's equal to my final momentum. So let's look at the final picture here. Here we have 2 cars of mass m moving at some speed v final. So what's my mass? Well, it's m plus m, or 2m. And what's my speed? Well, it's v final. All right, so I can add these together. I get 2m v final. And so now I can solve for v final by dividing by 2m. And look what happens. V final, I divide by 2m. The m's cancel, and I get 1/2 v. So simply put, when the cars collide, they travel at half of the speed that initial car collided with when they're equal masses. It's kind of intuitive. You might think that might be the result of this question. So, all right, but again, we're starting again when we solve these problems. We're starting with our conservation of momentum. We're defining our system. We're looking what things do I know about the initial momentum, what things do I know about the final momentum, and what variable do I need to solve. And these problems are really fun to solve. They end up working out really nicely, and they're not too challenging once you get the hang of them. Okay, so I've got 3 more examples, and hopefully, as we go through these, you'll actually be able to start solving them yourself. If you want to actually give that a try, we've done a couple examples. This one's a little bit different than the ones we've done, but I'd like you to maybe give it a try. So feel free to pause the video here, read this problem, see if you can figure out what's happening, and see if you can actually solve it, and then I'll go through the solution. So. All right, so if you were actually able to solve it, good job. And if you're just here to follow along, that's also fine too. And we'll look at what's happening here. So we have a 12,500 kilogram railroad car. And so we have our car of mass M travels alone on a level frictionless track with a speed of 18 meters per second. All right, and then what happens is as this thing is moving, so as this car is moving along the track, there is some other mass that's dropped into the car. So, I don't know, some other shipment that's being dropped into here. And so we're going to have original mass of our car, which we call M1, but we'll also have this additional M2 that gets added into the car. And if you think about what this is going to do to it, you should, think intuitively that the velocity is going to slow down because it's heavier now. And you would be correct in thinking that. But how much slower is this going to be? And we can actually use momentum conservation to figure this out. So here, again, we're going to start with this equation that P initial equals P final. Well, what's my system? Always define your system. So your system is going to be the railroad car plus the load that's going to be additionally added into it. In this problem, the load is not moving, right? Initially, it's going to be dropped into the car at a later time, but it doesn't have any momentum along this x direction. Yeah, it has momentum in the y direction, and we actually would want to consider that, but once it hits the ground, that momentum is absorbed by the ground. Really only looking in terms of the x direction, and so we're not super worried about that. Okay, so we have the system defined. So let's look at our initial picture. The car is moving at a speed of 18 meters per second and has a mass of 12,500. So we do 12,500 times 18 plus, and then our other mass is just 0, or our other mass is 5,750, but it's moving at a speed of 0. And so again, we can ignore that term. So if you don't have to necessarily write this in. Just want to show you that it is part of the system. We are including it, but it doesn't have any x direction velocity, so we're going to ignore it. All right, after the load is dropped into the car, the mass of this increases now. So now it's a combination of these two masses together. So our final momentum is 12,500 plus our 5,750 moving at some v final. And this is the variable that we're trying to solve for. And so you can pretty much just solve this out, and you multiply these together first and then divide by the added mass, add up the mass, multiply these together, divide that over, and you're going to get a velocity final of 12.33 meters per second, which intuitively we knew it was going to be a smaller velocity than 18. So we can get a sanity check here. Yes, this makes sense. It's moving faster. We drop some cargo into it. Now it's moving slower. That should be intuitive. Okay, so let's look at a couple more examples. Here we have a interesting problem. All right, you're having this dream about physics. You suddenly arrive in a dream where you're standing in the middle of a frozen lake. In a desperate attempt to move to the dry land, you decide to throw your 6-kilogram backpack towards the west end of the lake at 2.5 meters per second. Calculate how fast you'll move in the opposite direction if you have a mass of 65 kilograms. So the idea here is we're going to assume that we have zero friction between ourselves and the frozen lake, and it's a dream, so it's fine. We can make that assumption. So here we have you standing in the middle of this frozen lake, and you're in a dream, so you don't really know how you got there. But you do have a backpack, so that's good. And so you take your backpack and you give it a nice toss this way. And your backpack flies off this way. And just like the gun that fires the bullet, you'll actually cause yourself to recoil. And you'll cause your actual self to go this way as the backpack goes this way. And yes, this would actually happen. There was a movie that came out, Gravity. Some of you might have saw it. And at one point, she is steering herself in space using the air pressure from her suit or fire extinguisher or something like that. And that is the same idea here. Basically, there's no friction, and so any force exerted on you is gonna, move you in some direction. And so the idea would be, if I toss the backpack this way, then I will slide to the right. And let's calculate how fast our dream velocity would be. Okay, so it's a similar idea as all the other ones. We're going to start with our P initial equals P final equations. For your initial momentum, well, again, what's the first thing we have to do? We have to define our system. So our system here is going to be our self and the bag. Initially, what's your momentum? Well, you're standing in the middle of the frozen lake, you're at rest. So initially, our momentum is 0. And you don't even have to plug in there. You could say, okay, my mass is 65 times my velocity is 0 plus the mass of the bulk bag is 6, velocity is 0. Don't waste your time writing that out. If you know the momentum is 0, just write it out as 0 equals. And now, what's happening in the final picture? Well, in the final picture, we have the backpack moving to the left. We have thrown our 6 kilogram backpack in the negative direction at 2.5 meters per second. There's our units for momentum. It's in the negative x hat direction. And our person, has a mass of 65 kilograms and has some final velocity, which we're trying to figure out. All right, and so this simply becomes multiplication here, 6 times 2.5. Add this over to the other side or subtract it over, but it's negative, so it'll be positive over here. Divide by 65, and you're going to get a positive answer of 0.231 meters per second. And again, this is going to be in the positive x hat direction. So our velocity vector will be off to the right here, and we'll be moving at a pretty slow speed. But if there's no friction, we'll eventually get there. And so the idea is sound in this weird dream that we're having. Yeah, tonight everyone's going to have dreams about being on a frozen lake. You're welcome. You're welcome. All right. And finally, our last problem for the day. Here we are. It says a 2 kilogram wooden block is initially at rest on a frictionless surface. A 13-gram bullet traveling 230 meters per second penetrates the block of wood and emerges going 170 meters per second. So this time, unlike our other example, when we had our bullet firing at the wooden block, this time the bullet actually goes all the way through the block. That was weird. Sorry about that. So this time, the bullet goes all the way through the block, and it comes out the other side. Right? And so initially, the bullet is moving at 230 meters per second. And over here, it's moving at 170 meters per second. So it's slowed down a little bit as it's gone through, which you would expect. There's some friction there. And but what we should also see is the the big wooden block should have a velocity after this collision. Okay. And so we're going to, again, use our P initial equals P final equations as we've done in all these problems. So what is our system? Well, our system is going to be the bullet and the block. All right, so the block has a mass of 2 kilograms. The bullet is quite tiny, has a mass of 0.013 kilograms. Make sure you convert these to kilograms so they have the same units. 13 grams is, slide the decimal place. So we have our initial is going to be the bullet traveling toward the block, and our final is going to be both moving after. So initially, we have our bullet moving at 230 meters per second, and our block at rest. So I'm not going to write that in, right? It would just be 0. And then after, we have our velocity of our block. So we have a 2 kilogram block. Not write the units in this time. We've seen the units work out. Moving at some velocity, which we are trying to figure out. And we have our mass of our bullet again, 0.013 plus or times 170, our velocity of our bullet final. And so again, you can kind of see this pattern emerging here. We do initial and final, and then we have to solve for some variable in here. So you can just simply take our momentum here and our momentum here, subtract them from one another, and then divide by 2. And you'll see that the V final for the block is 0.39 meters per second. So again, not moving that fast, but it does have some speed. All right, so that's it. That's it for our momentum and introduction problems. And so hopefully you guys enjoyed solving some of these problems. I'm gonna give you guys a problem set to work through some of these. And yeah, I don't think they're too challenging once you get the hang of it. But just as a quick review, remember always start with initial and final momentum being equal to each other. Define your system, helps to draw a picture, and then just use your momentum equals mass times velocity. Think about which ones have a 0 velocity. You can ignore those ones initially. Write out your equation and then solve for your unknown. All right. Have a great rest of the day. I will talk to you guys soon.